Everyone, great pleasure to introduce Ameer. Ameer, it's quite amazing. He actually, I don't know about Kirst, I haven't had a student graduating so fast and being actually so productive in such a short time. And Ameer is the kind of guy, it's almost like nothing is impossible. So, and has done a lot of work on bringing machine learning to compiler optimization and hardware optimization. So it's looking forward to his talk. I'm not sure, Krista, do you want to say anything?
No, I think you're 1 year short of my previous record was Emmett. I think he was you're a year better than him. So pretty cool.
Okay.
Yeah.
So you can take it from here.
Yeah.
Sam.
Okay. Can you see my screen?
Yeah.
Okay. Let's see how I can hide this. Is there a way? Hide and hide this. Okay, great. Thanks, Jon, for the intro. That was a great intro, actually. Thank you for that. So yeah, thanks everybody who came here and joined my talk. And today, basically, I'll be showing you how we'll be using, or how we use machine learning and compiler optimization, mainly deep reinforcement learning. And I would like to start with motivation. So as you all know, with the end of Moore's law, for those of you who don't know what Moore's law is, basically it states that every 2 years we can double the number of transistors on the chip and therefore double its performance. And now we're reaching the physical limitations of that, which prevent us from actually doubling the performance every 2 years. And as a result of that, what we have been seeing recently is a lot of application-specific integrated circuits, a lot of new technologies, and a lot of new different architectures of chips. And of course, we're in an era with a plethora of new applications in robotics and healthcare, cryptocurrency, AI, of course. And unfortunately, all these programs or applications eventually have to run on these continuously changing architectures. And for that to happen, we basically have some intermediate layer called a compiler, which is basically a translator that translates this high-level code to the binary or assembly that would run on hardware. And as you can see, with all these applications and all these target hardwares, it becomes very confusing for the compiler to optimize for performance for different target hardwares. So basically, the objective is to be able to compile applications to rapidly changing hardware and software without compromising the performance. And to do that, we basically built more intelligent compilers. With such compilers, we actually benefited in two aspects. First, we were able to continue the scaling of Moore's law in a much cheaper and faster to realize way. And second, we made the life easier for the programmers, to transition for new customized hardware and for new applications. So how did we do that? In TLDR, basically, we observed how a compiler optimization task can be formulated basically as a Markov decision process. Most of the compiler optimization tasks can be seen as an MDP, where the state is the compiled program, and the actions are basically the next optimization to apply. And the reward is the performance improvement. So you can think about that all these states that we have here are basically the program after compiling it. And then, we take actions to transition between those that are different compiler optimizations, and we get a reward for improving the performance. And with this view, we started with targeting the very basic and first problem that the compiler has to deal with. which is known as the phase ordering. So when you compile a program, you have to tell the compiler, or the compiler has to figure out which optimizations to apply and in which order to apply them in order to get the best performance. And apparently there are more than 2 to the power of 247 possibilities. For example, in the LLVM compiler and in GCC, there's more and more than that. And for this particular problem, we built a system that we called AutoPhase. AutoPhase uses deep reinforcement learning for solving this task. DeepRL is one of the very promising and evolving techniques for solving MDPs. And we started with DeepRL with AutoPhase. And then, we realized, within each of these optimization, actually, we can tune different pragmas or provide different parametric values that also impact the performance. For example, vectorization, interleaving, and unrolling, and things like that. And for that, we built NairoVectorizer, which also uses DeepRL to optimize this task after we have the best orderings. And then later, we wanted to do more and more optimizations higher up in the stack that involve higher level compiler optimizations that require scheduling, reordering, and things like that, multi-threading and things like that for every section of that code. And for that, we built ProTuner, which uses Monte Carlo tree sage, which is also one of the promising methods for solving MDPs to address this task. We have taken this actually a step further. We have used DeepRL for things that are more than just compiler optimization. We got to a level where we can also, in runtime, for example, determine how much resources or cache allocation to allocate for different programs. I will not be able to go over this in this particular talk. I will cover mainly ProTuner, NairoVectorizer, AutoPhase, but you're welcome to check out how we can also do even a step further from here. So this is basically the motivation and some intro of what this talk is going to be about. Next, I will be talking about AutoPhase. So with AutoPhase, we basically built a framework that uses deep reinforcement learning to address the phase ordering challenge. We performed an importance analysis on the features to understand which features were more fundamental to the performance and which passes or optimizations were more important. And we showed that it can generalize to different workloads and achieve 28% better performance over -03. So let's go back to explain the problem to you. Basically, when you compile a program, you generally give it the compiler and then the program, and there are a bunch of flags here that determine basically which optimizations the compiler has to perform and in which order it has to do it. You can think about it that it's like loop unrolling, inlining, and things like that. And this is very critical to the performance, but at the same time, there are so many possibilities that nowadays we basically use predefined or a static sequence of flags known as -03, for example, or -02. But in reality, we can get much better performance than -03 by manually or by trying to figure out, even random search for a while can figure out this thing. Now, if we look at the related works that try to solve this issue, there are many related works that are there. I just summarized a few here, but there are a lot of related works, and I can summarize them in two categories, basically heuristics or greedy algorithms or genetic algorithms. And these kind of solutions are good. Sometimes they're very fast, but the disadvantage of these approaches is that they cannot really generalize. They don't really learn anything about the programs. Every time you have to rerun the search from scratch to get the performance or the optimization you want. And it's also error prone. Now, there are other methods that can actually learn and generalize, like supervised learning. But the disadvantage of supervised learning here is that it requires hard or impossible to find labels. that, you know, you have to label the performance for every sequence. With the enormous number of sequences, it will be very, very difficult.
Ameer, do you want questions now or at the end?
At the end.
Okay, cool.
Good. Thank you. So the ultimate solution is we want to be able to handle complex search spaces and decisions, and, you know, want it to be automatic with minimal hand engineering. We don't want it to require retraining. We want it to be able to basically generalize to new applications and new hardware. We want it to be feedback or experience driven. And by that, I mean that we actually compile the program and we actually run the program and measure real performance, not based on some guesstimate. And we don't want it to require labels, because this will make it take a long time to train, or even impossible. And this thing is basically available in deep reinforcement learning. So in deep reinforcement learning, we have an agent. You can think of it about, you know, a car driving on the street. This car or agent views the state of the environment. From this state, it takes actions in the environment. And to learn which good actions it should take, we can look at the rewards, which it collects by doing these actions. And what makes it deep is the use of a neural network to make the predictions on which actions to take. And actually, there's a growing number of RL applications in finance and system optimization, advertising, robotics. And, you know, as some of you know, in 2016, DeepMind showed AlphaGo, which beats the human champion in the game of Go using DeepRL. And in our context of phase ordering, if we go back to this agent, which previously, for example, used the gas, brake, steering for actions, and, you know, if it arrived at some good destination while it was driving, by observing the state based on the GPS location, it would get a positive reward. And if it, you know, got to some random tree, had a car accident, you know, you get a very negative reward because you got to wrong GPS location. You can think that in our context, instead of the car, we have some C++ or C source code. Instead of the gas or steering, we have the optimization passes like inlining, loop invariant code motion, et cetera, and then our output, or what we observe, is whether we have a fast code or a slow code, which is basically our reward, how much cycle count improvement we have. And our state is basically program features and the previously applied passes that we collect from the program and our history. Just to deep dive into how we generated these states, basically, we had our first kind of features were basically 56 static features that we got from the programs, like the number of instructions, the number of loops, number of branches, et cetera. We achieved that by adding an LLVM analysis pass that would output these values. And we also concatenated to that a histogram of previously applied passes. This was helpful in realizing which passes have been, you know, applied too much or not too much. Sometimes applying the same pass is useful, sometimes applying it is not useful. And this speeded up the training process. So the framework overall looks as follows. Basically, you can look here on the left. We have here the optimization passes that we, you know, applied so far, or let's say if we started from 0, we have here no passes at all at the beginning. And then here we have our input programs that are either randomly generated or real benchmarks. We compile the program and generate something called LLVM intermediate representation. This is, you can view this as this is the compile code that we observe. From this intermediate representation, we extract the program features with the analysis pass. We also have a cycle profiler that runs and measures the runtime, execution time of the program, which is basically our reward. And then, we feed that to our RL agent, which predicts which next pass we should apply. And here we aggregate these passes every time we apply one pass. There is a loop here that adds more and more passes. We have shown also that this is also feasible. This is also useful when you want to compile programs that end up generating hardware. So here we also added the support, for some HLS compiler that allows you to actually compile the circuit to real hardware. For evaluation, we evaluated a lot of other possibilities other than the DeepRL, and we compared it against random search, genetic algorithms, OpenTuner. OpenTuner achieved the best performance so far. Before we used DeepRL and a variety of greedy algorithms. And for our DeepRL, we used different methods like PPO, proximal policy optimizations, A3C, and evolutionary strategies. We mainly use methods that deal with policy gradient variant of the problem, because our task is episodic. It's not like continuous over time, it's predefined in advance. But we also used other methods like DQN, DDQN, and things like that that are not shown here. For our benchmarks, we used 9 benchmarks from Keystone. We used a simple 256 by 256 fully connected neural network. We limited the number of passes we applied to 45. And for the training, we used Ray and RLib and a simple CPU, GPU for training and inference. Let's start with some results. So what you see here is on the left, you see the performance improvement normalized to -03. -03 is the heuristic or the main baseline that most people use without knowing that it's happening, which is basically a predefined sequence determined by experts in compiler optimization that is there, that is supposed to work well for most of the hardware targets. On the bottom here, you see the different algorithms. And on the right here, you see how many times the program was compiled in order to achieve this performance. So first, let's look at the samples. You can see that, for example, for one configuration of our RL, we were able to achieve 24% better performance than -03 with only 88 compilations. And then, if you look at PPO3 here, we were able to achieve another 4% improvement over -03 with much less samples than the other algorithms. Now, you might wonder, okay, but the other algorithms like OpenTuner here also achieved a similar performance, of course, with more samples. And then, the answer to that is, let's look at the generalization. So we wanted to explore how well, our approach can generalize. And then, the question that we asked ourselves, is it possible to train a network and use it to predict the optimal sequence of any program in a single compilation? At the beginning, it was very, very hard because we had so many possible phase orderings. We had limited observations. So the program features that we collected from the program do not fully represent the state of the program. Actually, nobody until today knows how to represent a program in something that can be fed to a neural network. I heard some professors around say that it's a Turing Award-worthy problem. And we have limited data and our decisions are not explainable. So to try to address this issue, we looked at the actions and the states that we have, and we tried, to filter them out. So we built random forests for the program features and for the histogram of passes. Basically, we characterized each pass with random forests with the input as program features or the input as histogram of passes. And this allowed us basically to know which features are important for different programs. At the same time, it allowed us to know which passes were more important. And now for looking for some results, we see here the episode reward mean as a function of the number of steps or compilations we are at. So in red, you see here the original approach that took a very long time to train, and it was very noisy. But with two filtering approaches that we tried with different normalization schemes, we were able to converge much faster and achieve a much more stable result. And for our generalization, we basically trained on 100 randomly generated programs and inference on 13,000 randomly generated programs and the Chase-Stone benchmarks. For the randomly generated programs, we were able to achieve 6% better than -03. And with the Chase-Stone benchmarks, we were able to achieve 4% improvement over -03. And actually, -03 fails, for example, to compile the JSM benchmark. And if you look at the other methods like OpenTuner and genetic algorithm, it actually deteriorated the performance. And this actually showed us that there is a potential that we can learn how to compile appropriately with such a very, very difficult task. Now, I showed you now autophase, and next I want to show you the next step that we took after autophase, which is nairovectorizer. So just a reminder, with autophase, we compiled the program, we gave it a bunch of flags, and we wanted to determine which flags and in which order we should provide them. But the problem is actually worse than that, because we also have to determine, which factors or pragma should be provided for some of these flags. And for this, we built nairovectorizer, which is, of course, which appeared in CGO and is open source under the Intel nairovectorizer repo. So just to give you an idea, for example, for vectorization and interleaving, if we have here a code that adds two vectors together and puts the result in C. If we want to run this code sequentially, we would load one value from A, one value from B, add them up and store them. And that's what would happen in the second iteration. When we vectorize this code, we basically say, okay, we want to do these two loads at the same time, the adds at the same time, the stores at the same time. And this is something that is very compile time consuming. And it's very hard for the compiler to realize, which operations can be done together and whether to unroll the loop or whether, to interleave it. And therefore, today there is a very simple heuristic, for example, an LLVM that adds up the cost of instructions and tries to divide them up in some magical way that works fine for some programs, but for most programs it doesn't. And our contributions here were basically that we built a framework that uses DeepRL for automatic end-to-end vectorization. We achieved 97% of the optimal performance. And we showed that it can generalize to different workloads. So how the framework looks like. Our environment is basically a program. And this program basically, we detect all the loops from this program. And then, we generate the code embedding. We used two techniques actually here to generate the embedding. We used code2vec, which uses attention or a more complex model that translate code to a vector, or we just use the abstract syntax tree as a state. For our agent, we use PPO, which we found to be the best performing among all the other policy gradient-based methods. And then, our actions were the factors, the vectorization factors. You can determine here also other factors like unrolling or interleaving and things like that. You can look here, for example, VF and IF are generally 2 to the power of something, up to what the hardware supports. And our reward were basically the improvement in the reward over the baseline. So what the action of the agent is in reality is it's very, very simple. We look at this code, for example, and you can see here we're doing a dot product. So after detecting this loop, our RL agent will just enter a pragma that tells the compiler how to vectorize this loop, basically which vector width we should provide and which interleave count it provides. Now keep in mind that this does not change the functionality and does not introduce any errors, because if this might introduce some error, the compiler would just ignore it. And in most of the evaluated benchmarks here, this was not ignored. Actually, we were able to show that also the factors that were provided were legal and the agent was able to learn that. And with that, we evaluated our deep-RL algorithm. We only used PPO, again, because we found it to be performing the best. And we compared that to a lot of other approaches like brute force search or pulley, which uses polyhedral representation to compile the program, decision trees, nearest neighbor, et cetera, We trained on 5,000 synthetic programs, and we inferenced also on Polybench, MeBench, and the LLVM benchmarks. So I'd like to start first with the LLVM benchmarks. And you see here, on the left, the normalized performance for different benchmarks that are available on the vectorizer in this link. That is basically meant to test how well the vectorizer is. Now, if you look here, you'll see that we achieved 97 in GeoMean, 97% of the brute force solution, which took many, many days to run. And it's 2.67x better than using -03. So basically, if you use -03 today, you almost use 3x better, you almost get 3x worse performance than if you would run, some brute force search or, our deep-RL algorithm. But for those of you who noticed, you can also notice that the other supervised-based learning methods also achieved almost, 95% of that. And therefore, what's the point of using deep-RL? And here I want to go to the overhead in the number of compilations that we had to achieve this performance. So here on the left, you see the normalized average performance. And at the bottom, you see the number of compilations, basically how many compilations we had to do to get this GeoMean in performance. And basically, as you can see here, for vectorization alone, we were on a very simple vector size machine, we were able to get 14x fewer compilations with deep-RL. And actually with more possibilities of vectorizations and enrolling, this overhead actually multiplies. Moving on to transfer learning, where we trained the model and then we used it for inference. So first we inference on MeBench, which is not a highly vectorizable code. We just wanted to see if we don't actually deteriorate the performance of a code that is not highly vectorizable. And we compared it to Poly and the baseline, and here we were able to achieve roughly 10% better performance. But for applications that are highly vectorizable, like Polybench, where you have more matrix multiplication, more security, cryptocurrency, and things like that, we were able to achieve 33% better performance than Poly and 3.4x better than -03. And if you combine both of Poly and RL, you can actually get the best of both. And this here shows actually the average performance. You do inference 5 times and then you take the average. But if you actually take the best, which it's just 5 compilations, and take the best factors, you would get 1.85 better than Poly and almost 5x better than -03. Now, I just want us to keep in mind here that Poly does much more optimizations than just vectorization. It has loop reordering and tiling and things like that, that is somewhat giving an advantage to the Poly results here. If we would have taken them off, we would have been much better than Poly. So these are the results for Nairo Vectorizer. And next, I will be showing you ProTuner, which improves on top of Nairo Vectorizer to do more and more scheduling tasks. And here, we wanted to have for each section in the code, mainly for loops, to somewhat reorder it or tile it. You can think of it, it's also taking things from poly. It's also doing things that normal compilers wouldn't do. You would need, some compiler like Halide or 2VM that would generate actually the code or rewrite the code to allow us, to multi-thread it and do more tiling or fusion and scheduling to these tasks. And if we look at the most recent work that did this task, it actually used beam search. So what is beam search? Beam search basically starts from a program, and from this program, it checks all the possible optimizations from the current state. Let's say generated 5 possibilities here. From these 5 possibilities, it picks the top K candidates. How does it know which top K to pick? It basically builds a cost model that tries, to predict how long it takes to run each program. And then, from these 5 candidates, it generates the next, it generates the program, and from this program, we generate the next optimizations that can be here. We sort them, we pick the top K, and we keep repeating this process until reaching the end. The drawback, though, of using beam search is that it only picks the next states based on intermediate costs. The problem here is basically the program is not fully scheduled at the end. You can think about it that if the program has 5 for loops, at the beginning, the very first state is nothing. And then after 1 step, we have 1 for loop. And then after 2 steps, we have 2 for loops, et cetera, et cetera. So basically, we are evaluating here in the intermediate states costs that do not represent actually the program. You can have 1 loop that breaks all the previous costs that were before. It's intrinsically greedy. Sometimes, these decisions that we make are not greedy. Sometimes, you might add a for loop that in the short term, it gives, a worse performance, but in the long term, it gives a much better performance. And it requires evaluating a large space of possible schedules in the cost model. So you have to sort them, and then you have to evaluate a huge chunk of possibilities before you pick the top candidates. And it's not resilient to noise in the cost model, basically for the reason that the program is not unfolded. So the cost model is trained on incomplete programs. Now, if we ask ourselves, how can we improve the search in this case? First, we want to be able to look ahead before making a scheduling decision. We want to avoid this greediness. Basically, looking ahead allows us, to make better decisions because we're looking at the long term rather than the short term. And if we avoid the greediness, we also basically are looking ahead and making sure we make smarter decisions. We don't want to make these decisions on intermediate, incomplete states. And we want to be able to be resilient to noise in the cost model. Now, our inspiration came from looking on how beam search basically explores and unfolds the next states. We saw, it was very good, but we wanted to be able to do all of our things that I mentioned here. We want to be able to look ahead, evaluate, and then backprop. And this is something, that comes built in Monte Carlo research or MCTS. Now, before I describe basically what we used MCTS, we also used other methods that involved, evolutionary algorithms with a learned cost model, which appeared in OSDI, that you can also feel free to look at the other method there. Now I'll just describe the method that uses Monte Carlo research. So Monte Carlo research has 4 steps. Basically, first you start by selection. You recursively go down in the tree, picking the best candidates so far. And then when you pick this sleeve, you expand it. You add 1 more node, and then you run 1 random simulation from that node. And then after you did this simulation, you backpropagate the values that you collected or the reward to update the nodes. I will deep dive into what is exactly happening in each step here in the next slide. So our contributions are basically we proposing to formulate the scheduling problem as an MDP, again, Markov decision process. This time we solve it with Monte Carlo tree search. We build a framework that uses MCTS to schedule programs, and we outperform beam search on all the benchmarks. So how we formulated the MDP, now that you're more familiar what is an MDP with agent and environment, basically we determine the reward to be 1 divided by the execution time. So the longer the execution time, the worse, and the shorter the execution time, the better the reward you have. Our state is basically based on program features and schedule features, very similar to the beam search work. And our actions are all the actions that I showed you in previous slides for tiling, vectorization, multi-threading, inlining, etc., etc. And from all of these combined together, we combined it in MCTS. So the MCTS that you have here, basically, we start from the root. On the left of each node here, we have the best cost from this node. For example, if you have here 2, it means that the best possible value that we got here is 2, which is this 2. If you have 3 here, it's 3. If you have 3, like from all the children, the best was 3. And 5, or the value on the right, is basically the average of the rewards we collected here. And the advantage of this approach is that we do not really evaluate the cost on all these intermediate steps. We just wait for unfolding the program. And then at the very end, we evaluate on fully scheduled programs with the learn cost model, and we backpropagate that. We backpropagate the average here on the right, and on the left, we store the best. And we search using the upper confidence bound. We expand the child that maximizes the upper confidence bound, which is guaranteed to converge after a very, very long time. And it's very resilient to noise in the cost model because we are looking here at average, which also makes us more and more careful. And with MCTS, if we started in this route, for example, then instead of picking after we finish the search, and now we want to determine which node or which optimization we're gonna take, we look at all the children after the search has finished for this particular node, and instead of taking the average, we take the best. We found this to outperform taking the average because in general we just wanted the best performance. So one advantage of MCTS is that there's a work that showed that if you use an ensemble of MCTSs, it can outperform a single MCTS, or at least achieve the same performance of MCTSs. And this basically allowed us to parallelize this task over multiple cores or multiple machines that allow us to search and investigate much, much, much faster. So for our evaluation, we ran on M5-8X large instances. We used hyperthreading. We turned off the hyperthreading because we did not want the programs to interfere. It also reduced the noise and variance. We put the limit to picking a new route to 30 seconds. At the beginning, we also played around with that. So basically, for every optimization decision we want to make, we spend 30 seconds searching, and then we make it. And we compared it to beam search. We used the open source code, and we ran basically 16 beam searches in parallel for apples to apples comparison. And we took the same benchmarks from this work, which is under the Haj-Ali repo. For some results, we have here 16 benchmarks comparing only MCTS and beam search. For most of these applications, we either achieved the same performance or we outperformed it by up to almost 3x. But then, we wondered maybe we can actually do better. So if you look at this MCTSs, when you run them in parallel, basically you determine the next route to be the best of the best. But instead of picking the best of the best based on the cost model, what we did instead, we basically compiled the program and picked the best real execution time. So instead of using the cost model to make the final or at each intermediate step after 30 seconds or a predetermined number of seconds, we actually compiled the program and picked the one that gave the actual execution time. And now our results here looked even better. So what you see here is on the left, you see the execution time, the y-axis is basically the execution time speed up, and for the different benchmarks. And we have here many configurations. So first we use the code from master, which you see here in blue. We also ran random search because they also ran random search. We ran also greedy algorithm that they proposed, which is basically a beam search with a beam size of 1. And then we explored different MCTS configurations. We mainly played with the exploration to exploitation ratio. We played with how long it takes for making each intermediate decision, and for whether we are including the real execution time and or not. So there are things that we ran that we did not take at all the consideration of measuring actual execution time, and things that actually took the real execution time. And the TLDR here is that if you look at the mean in our best configuration, we were able to achieve 36% performance better than beam search. Now, if you wonder, how long it took to achieve these results, and for that, we time bounded the search time for beam search or the MCTSs to 15 minutes. And we ran something called auto-tuning, where basically, you run the search once until, you reach the time budget. And, over and over, you collect data and you pick the best at the very end. And here also, we were able to achieve a very similar performance improvement in total, 36% in the same time budget. So so far, I showed you autophase, nairovectorizer, and I showed you now a pro-tuner. And with that, I want to conclude my talk. So the TLDR of this talk is that ML and compilers, mainly DeepRL and MCTS and algorithms like that, is necessary to keep up with the Moore's law and the continuously changing hardware and software. I showed you how we can, formulate many compiler optimization problems as MDPs and solve these MDPs with MCTS and DeepRL. And we showed that MCTS and DeepRL outperform state-of-the-art methods. For acknowledgement, I really want to thank everybody here who helped me. Of course, my advisors, my committee, my main collaborators at Berkeley. Special thanks to Jenny for working on many of these projects with me, of course, Hassan and William, and the Adept Lab members, Rise Lab. What is great about Berkeley that, have all these geniuses around you that you can continuously learn from people and get some motivation and focus on things that are beyond brilliance and being smart, because everyone's smart. So to focus more on, teamwork and learning and, getting together and how we can build these huge projects together. And, of course, my family and everyone else who supported me. And that's basically it. Thank you.
Thanks a lot, Ameer.
Yeah, thank you. It was 42.37 minutes, which is, in the range that I gave you, 42.
That's good. We were gonna fail you if you were outside the range.
I thought that I already passed, right? Because
that's true. We already signed.
You never know.
All right. So should we take questions now?
Yeah, I'll be happy to take any questions.
I had a question about autophase.
Mm-hmm.
did you run it on any longer benchmarks like spec or like the Linux kernel or something? And did it show similar results?
Yeah, so we ran it on some, applications like the GCC compiler, which is something, that happens over and that are not shown here. We ran it like specifically for these tasks. We were able to achieve better performance. We didn't report the performance here, but keep in mind also that many of the Chasestone benchmarks are also similar to what is in the spec. But yeah, that's a good point. Like for narrow vectorizer or LDRM, we were like definitely did that. For here, it was just cherry picking some benchmarks. Does that answer your question?
Yeah, thanks.
Oh, thank you. Any other questions?
So you had mentioned this earlier about kind of methods that can learn from sort of multiple programs versus have to do everything from scratch for each program. I was wondering, so like if you apply, you mentioned genetic algorithms. So I agree if you like apply them directly, to like a program, it's going to have to learn from scratch. But you could imagine like trying to apply genetic algorithms at the level of just the compiler optimizer. For instance, if it's just sort of in general, there's different ways you could interleave different heuristics, and some of them work better on average. You could try to learn that. I don't know, is that something that people have tried, or are there reasons it wouldn't be a good idea?
So for our generalization result of these algorithms, we did something similar to what you're saying. We tried, to run search on multiple programs in parallel, take the geomean, and this is a predefined value, and we applied it to all the programs, and it did very terrible. But using in particular all these heuristics together without a cost model, sure, it would get you the same performance, but are you saying that we can use that actually to not search from scratch?
Well, like so let's just suppose we take GCC, right? And it does well. I guess maybe this is what you're already doing. I was just thinking like GCC applies different optimizations in different orders, and it has some default ordering, but maybe there's like a different ordering that's better as the default, and you could try to learn that with a genetic algorithm. But I guess you're already sort of figuring out the right ordering, so maybe that this is just going to be worse than whatever you did.
Yeah, we somewhat did that, and the results that I showed here for generalization of autophase does basically what you're saying. It's trying to learn a better -03, right. And the TLDR was that in most cases just performs much worse.
Right. Okay, got it. Thanks.
Okay. Welcome.
I have a question also on autophase. First, thank you for the talk. It was a great talk, and you did an awesome work. It was really fantastic.
Thank you.
Yes. And on autophase, so you have these 24% of speed up with the 88 compiler compilation of your program. I'm not sure to have understood if you are allowed in your process to change the ordering of the passes, or if you just stack the passes one after the other.
So we stack the passes one after the other. That's how we formulate the MDP. So after every step you add one pass, you change the program. But the point here, the advantage of why we were able to achieve here, you said here why we have like 88 compilations very fast. So with this kind of configurations for PPO, actually we did not have to compile the program at every step because our features were only a histogram of previously applied passes. So this way you can basically take many actions, and since you're using something like policy gradient or PPO, you only need the reword at the very end. So this basically allows you to do a bunch of optimizations, but only compile once. And that's why.
Okay, so it's 88 compilations, but it's not only 88 passes. Like
it's not 88 passes, definitely.
Yeah.
It's like many, many passes.
Yeah. Okay. And do you think if you allowed your process to reorder the passes or to maybe to remove some things from the stack because it took, is it possible that it took a wrong path and you could get better results? Or?
So yeah, if it took the wrong path, it means that this would have affected the program performance, or the execution time would deteriorate, and then the reward would be bad, and then you would update your model to know that you should not take this action in the future.
Yeah, I mean the wrong path, not in terms of direct performance, because of course you're always increasing the performance, but maybe not the best path. Maybe if you add some more compiler paths behind, from some state you can get into a better performance than from another. I don't know if it's possible. Like maybe.
Can you clarify the question? I still do not fully understand. Like you're saying we set a predefined set of passes and start from there, or what?
So yeah, my understanding is that you're basically searching a tree of compiler passes, or of combination of compiler passes. Mm-hmm. And you're going inside that tree to the best node where you have the best performance for a certain number of passes in a certain order.
The deeper, you can view this DeepRL as, you know, a tree, but the use of the tree there was just to filter the features and the histogram. Sorry, maybe I did not clarify it. But you know, we use the trees just to, you know, filter them out and pick the best passes, but we still used RL on the new filtered passes.
Okay. But, so you're sure that you're getting into the best performance you can have with this number of passes?
There's no way we can know that this is the best, right? Because you know, it's to the power of bajillion, so you can't really know if it's the best. But you know, heuristically, we didn't find any algorithm that we ran that could achieve better. I know it doesn't promise anything, and I think there is still room for improvement. But yeah, there are many things that I didn't go also into detail here. For example, we found that passes should be applied in a particular order, or maybe applying a pre-passes at the beginning to start from, or maybe starting from -03, or maybe instead of doing phase ordering per pass, we did pace orderings per chunks of passes. But yeah, the only one that we found to be just good straight away and was performing better was just to make it optimized per pass rather than, you know, chunks. And sometimes, you know, giving the pre-passes was helpful, actually.
Thank you.
Yeah, thank you.
I have one more question. Do you think this would be accepted upstream in LLVM as a new OML or something, you know, a different optimization level where it uses something like this?
I think in the short term, no, and the long term, yes. So, for example, when I worked at Narrow Vectorizer, I was at Intel. I was working with the Intel people there, and they basically proposed what kind of problems. We have used it actually for some stuff that I can't talk about within Intel. But we always had this blocker of, okay, can we explain to our customers how we got this performance, or why is it performing like that, and how, you know, all these kind of questions that we couldn't really explain. Maybe with random forest we were able to show that it's happening, but it seems like in general this is transitioning. Like with Halide, they were very passionate about it, and they, you know, accepted it, and you know, we can just merge the branch with Anzer. Also, I think it's also open sourced in the TVM repo. But for autophase and the so what remained basically is autophase, because the other ones are fine. I think it will at some point definitely be something that they will just have to use. I think the only caveat here is that we have to add some layers of guarantees, or some way that if this performance was not good, we will have other heuristic, for example, for programs that we haven't seen before. But I definitely see that happening, especially, for example, with ML-IR, which was introduced also in LLVM, which allows you, to apply any ML methods inside there. It's actually evolving very, very rapidly.
Okay. So I think congratulations. I think again, Ameer.
Yeah,
Many
thank
congrats.
you. Thank you.
So do we call him Dr.
Dr.
Ali now?
Please file his thesis.
Yeah, thanks everybody who came. Look at the time, it's just exactly 3.
Yeah.
It's even with late, we took care of the late time.
Thank you.
Thanks,
Thank you.
Ameer. That was a very nice talk.
Yeah, thank you.
Congrats again, Ameer.
Thank you.
Congrats.
Congratulations.
Okay, bye-bye.
Thanks for coming. Thank you.